What's going on, everybody? Got a video here for you. This is differential equations, and we are going to go over definitions and terminology. Now, you might not think, this is a very important section, but it is. We're not actually solving differential equations in this one. We're just kind of learning the terminology and getting familiar with everything. It's important. It'll help you as you go through the class. All right, so we've got definition, differential equation, an equation containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation. And if you see this DE, that's what I'll use to abbreviate differential equation. All right, so let's just look at some of the types of differential equations. So for the first kind, let's look. We've got dy dx plus 5y equals e to the x. There's a differential equation, and we'll get into more of what these things are called as we go through the lesson. And another example of a differential equation. Oops. There's another differential equation. All right, and then we might have something like this: dx dt plus dy dt equals 2x plus y. There's one. All right, and now this right here, this ODE, that's an abbreviation for ordinary differential equation. It can contain more than one unknown function. You can see there. All right, and these are examples of ordinary differential equations. All right, now let's look at B. Let's say we have this, and let's look at this one. And then let's look partial u partial y equals negative partial v with respect to x. And these are examples of partial differential equations. Okay, and I know this this video or this lesson may not be that exciting to you. May be, boring. We're just looking at this definitions and stuff, but I'm telling you, it's important you watch this video. And so these are examples of ordinary differential equations, and these are examples of partial differential equations. There are some sections in the differential equation book that has some partial differential equations, but I don't know if you're going to cover that in your class or not, but they do have an entire class on partial differential equations. You might be interested in taking that one. So let's look at the notation. So we've got Leibniz notation. That's where we would write the derivatives like this, dy dx, and then second derivative of y with respect to x, and third derivative, and so on. And then we've got the prime notation. We got y prime, y double prime, whoops, and there should be a y there, y, whoop. That should be y triple prime. Okay, so that's just different notations there. And so if you have like here we have the second derivative of x with respect to t. The x here, that's your unknown function or your dependent variable, and the t is your independent variable. Okay, so just things you need to know. And then we have dot notation, Newton's dot notation. So if you've got the second derivative of s with respect to t equals, say, negative 32, we can write it the s, and for the second derivative we would put the two dots over the s is equal to negative 32. Okay, and we saw the partial differential equations up here. So, we're going to look at, let's just look at this right here. We wrote it down here again. So partial derivatives can be denoted by a subscript notation. And so if you have this as your partial differential equation, you can write it like this. Okay, this is another way to write this equation. Okay, just the different notations. Say this would be the second derivative of u with respect to x. This is the second derivative of u with respect to t minus 2 times the first, and I say derivative, I mean partial. And this would be the first partial of u with respect to t, second partial of u with respect to x, second partial of u with respect to t. Now let's look at the order of a differential equation. Either I left off the r there. Either an ordinary differential equation or partial differential equation is the order of the highest derivative in the equation. So if you're looking at this, you can see that this first one right here, this is a second derivative, and this second right here, this dy dx, that's a first derivative. So this would be a second order, this would be a first order, and this ordinary differential equation here, it is a second order ordinary differential equation. Okay, it's the highest power there. Or the highest derivative. Now let's look at an example. We've got differential form of a first order ordinary differential equation. If we assume that y is the dependent variable in a first order ordinary differential equation, then recall from calculus, dy is defined to be dy is equal to y prime dx. So we're kind of looking at the form of a differential equation. So let's just say we have the differential equation y. What's going on here? Had some technical difficulties there. I had to reboot my program. All right, so if we look at a differential equation, say y minus x dx plus 4x dy equals 0. There's different ways that we can write these differential equations. For example, we could divide everything, divide by dx, and if we do that, we would get y minus x plus 4x dy dx is equal to 0. Okay, and then if we move the x to the other side, okay, we would have 4x dy dx plus y equals x. This is just another way to rewrite this differential equation here. And then if we look at, let's look at this one, 6xy dy dx plus x squared plus y squared equals 0. Okay, well, let's multiply everything through by dx. So if we do that, we're going to get 6xy dy plus x squared dx plus y squared dx equals 0. Okay, and then, you know, this, we could write this as x squared plus y squared, and we could factor out a dx plus 6xy dy is equal to 0. So there's another form that we could write a first order ordinary differential equation. Okay, so you'll see as you go through the course that's one thing that you may have to do is rewrite the differential equations into a different form to solve it. All right, so that's just some stuff right there. All right, so here it says in symbols we can express an nth order ordinary differential equation in one dependent variable by the general form this. Okay, f of x, y prime, all the way to the nth derivative of y, where f is a real valued function of n plus 2 variables, x, y prime, and so on. It is possible to solve an ordinary differential equation in the above form uniquely for the highest derivative, the nth derivative, in terms of the remaining n plus 1 variables. The differential equation, this, okay, notice in this one we went to the nth derivative, but here we go to the n minus 1 derivative, and you've got the nth derivative over here by itself, where f is a real valued continuous function, is referred to as the normal form of this, of f. Thus, when it suits our purpose, we shall use the normal forms. And basically what you're doing is you're solving for the highest derivative. Okay, and so see here you would have dy dx is equal to f of xy. And then if you have the second derivative, you would have something like f of xy, y prime, to represent general first and second order ordinary differential equations. This would be a first order, this would be a second order. All right, so let's look at this. We've got an example here. This is the normal form for an ordinary differential equation. Okay, so if we have, let's say we have 4x, we'll call this part A. If we have 4x dy dx plus y equals x. Okay, so let's put this in the normal form. So we're going to solve for dy dx. So we would get 4x dy dx is equal to x minus y, and then divide everything by 4x. So we get dy dx is equal to x minus y over 4x. This is the normal form of a first order differential equation. And then what if we have something like this? Y double prime minus y prime plus 6 equals 0. Well, if we solve this, we're going to get y double prime is equal to y prime plus 6. And this is the normal form of a second order differential equation. Okay, so that's the normal form of an ordinary differential equation. Okay, you're solving it for the highest derivative there. All right, classification by linearity. An nth order ordinary differential equation, this f, is said to be linear if f is linear in y prime, and the nth derivative of y. This means that an nth order ODE is linear when f is equal to this or this. All right. So I'll explain this more when we show the examples and all that stuff. Okay. Two important special cases of the above equation are first order n equals 1 and linear second order n equals 2 differential equations. And here's an example of a first order, and here's an example of a second order. Notice the dependent variable y and all its derivatives, y prime all the way to the nth derivative of y, are of the first degree. That is, the power of each term involving y is 1. Okay. The coefficients a0, a1 to a sub n of y prime, and the nth derivative of y depend at most on the independent variable x. Okay. So does that make a lot of sense there? All right. So if it does, that's great. If it doesn't, let's look at these examples and maybe it'll clear some stuff up. All right. So let's suppose, let's see, part A, we have y minus x dx plus 4x dy equals 0. We have y double prime minus 2y prime plus y equals 0. And then we got, let's see here, x cubed d3y, that's the third derivative, plus x dy dx minus 5y equals e to the x. Okay. Now, all right, these are all, well, this is a first order, this is a second order, and this is a third order linear differential equation. Okay, and you can see, like for example, this one. If we, let's say we divide everything by dx, that would give us y minus x plus 4x dy dx is equal to 0. And so that would give us 4x dy dx plus y equals x. And what does it say for linear? The dependent variable y and all its derivatives are of the first degree. That is, the power of each term involving y is 1. You can see there's a y there. That first power there is a 1. Okay, so you can see it a lot easier when we get it into this form here. Okay, might be a little more difficult to see in this form, but maybe you do see it. All right. And then for part B, let's look at this. We've got 1 minus y prime plus 2y equals e to the x. Then we've got the second derivative of y with respect to x plus sine y equals 0. And then we've got x cubed d3y dx cubed plus x dy dx minus 5y equals e to the x. All right, these are all non-linear. Okay. All right, so this is a non-linear term right here. Okay, the coefficient of y prime depends on y. Okay, and then of course we know that's not linear. That's a non-linear function of y. That's your non-linear term. And then, let's see. Oh, you know what? I didn't write down the right equation here. My bad. Let's see. We got d4 y dx 4 plus y squared equals 0. So obviously you can see this is nonlinear. See how the y term is squared? And these are nonlinear differential equations. This is a first order, this one is a second order, and this one is a fourth order. All right. So, excuse me. So hopefully that kind of clears this up, what we wrote here. All right, definition. Solution of an ordinary differential equation. Any function phi defined on an interval I and possessing at least n derivatives that are continuous on I, which when substituted into an nth order ODE reduces the equation to an identity, is said to be a solution of the equation on the interval. You cannot think solution of an ODE without simultaneously thinking interval. The interval in the above definition is variously called the interval definition, the interval of existence, the interval of validity, or the domain of the solution, and can be an open interval a to b, a closed interval a to b, an infinite interval a to infinity, and so on. Okay, it's over an interval. So let's look at an example. We're going to verify solution. So it says verify that the indicated function is a solution of the given differential equation on the interval negative infinity to infinity. All right, so we've got the differential equation here, and this is what they're saying the solution is. So what we want to do is we want to take the derivative. So we want to find dy dx. Well, that's going to be what? 1/4 x cubed. We're just taking the derivative of this. And then what we're going to do is we're going to plug this into the derivative, and we're going to plug this in for y. So we've got 1/4 x cubed is equal to x times 1/16 x to the 4th raised to the 1/2. And so we get 1/4 x cubed is equal to x times, and then when we square root that, that's going to be 1/4 x squared. And so this is going to give us 1/4 x cubed, which is this, and then when we multiply, that's going to be 1/4 x cubed. And so we verified that as a solution. And then the same thing here. If we verify this, we can get y prime is equal to the derivative of the first function times the second plus the first function times the derivative of the second, which that's going to tell us that y prime is e to the x plus x e to the x. All right. And then the second derivative, well, that's going to be e to the x plus, and then we got product rule here, 1 times e to the x plus x e to the x, which tells us that y double prime is e to the x. Well, let's write it like this, equals 2e to the x plus x e to the x. So there's your first derivative, there's your second derivative. And then we're just going to take it and plug each one in. So we got 2e to the x plus x e to the x minus 2 times y prime. Y prime is e to the x plus x e to the x. And then plus y, which is x e to the x. And we need to make sure that equals 0. So, I mean, I'm not going to go through and do all this, simplify it. You should be able to do that by now. But if you simplify this side, you're going to get 0. And you will get 0 equals 0, which would verify that solution. Okay. If you struggle with doing that, then you might have problems in the class, right? If you've come this far. All right, solution curve. The graph of a solution phi of an ordinary differential equation is called a solution curve. Since phi is a differentiable function, it is continuous on its interval, I, of definition. Thus, there may be a difference between the graph of the function phi and the graph of the solution phi. And here's an example. Here's a graph of the function y equals 1 over x, and we know x cannot be 0. Well, we may be looking at a differential equation on the interval 0 to infinity, and this would be your solution here over the interval 0 to infinity. And that's what they're talking about there. This would be the graph of the function, and this would be your solution here. All right, so we have definition, implicit solution of an ordinary differential equation. A relation g of xy equals 0 is said to be an implicit solution of an ODE of an interval I, provided that there exists at least one function phi that satisfies the relation as well as the differential equation on I. All right, so that's an implicit solution. Let's look at an example. Let's say we have the relation x squared plus y squared equals 25 is an implicit solution of the differential equation dy dx is equal to negative x over y on the interval negative 5 to 5. All right, and we can verify that. We can find dy dx here and plug it into here. So if we take the derivative of that, that's 2x plus 2y dy dx, do an implicit differentiation, equals 0. So that's going to be 2y dy dx is equal to negative 2x. Move the 2x over, divide both sides by y, we get dy dx is equal to negative x over y. And you can see if we plug this in for dy dx, that's going to match the right hand side. Okay. All right, so let's look at this. Let's solve x squared plus y squared equals 25 for y. Okay, and so if we do that, we get y is equal to plus or minus the square root of 25 minus x squared, right? And so you saw that we had this implicit solution up here, but look at this. The two functions y equals, we'll call this phi 1 of x is equal to the square root of 25 minus x, and y equals, let's say, phi 2 of x is negative square root of 25 minus, well, not minus x squared. All right, so we've got two solutions. They satisfy the relation. That is x squared plus phi 1 squared equals 25, and x squared plus phi 2 squared equals 25. We can plug each of these in for y here. Okay, that's what that's saying. And are explicit solutions defined on the interval -5 to 5. Okay, and let's just look at this. So here is an implicit solution. Of course, that's 5, 5, -5, -5. This is our implicit solution. X squared plus y squared equals 25. And then we could have this one. Well, what is this one? That's -5 to 5. This is explicit solution. This would be y1 is equal to the square root of 25 minus x squared -5 -5 to 5. And then we would have this solution, -5 to 5. This is an explicit solution, and this y2 would be negative square root of 25 minus x squared. X is between -5 and 5. All right, so let's look at this. It says a solution of f of x, y prime equals 0 containing a constant c is a set of solutions, g of x, y, c equals 0, called a one-parameter family of solutions. When solving an nth order differential equation, we seek an n-parameter family of solutions, g of x, y, c1, c2, all the way to cn equals 0. A solution of a differential equation that is free of parameters is called a particular solution. All right, so let's look at some of these examples. All right, particular solutions. So part A, we've got for all real values of C, the one parameter family y equals cx minus x cosine x is an explicit solution of the linear first order equation. X times y prime minus y equals x squared sine x on the interval -infinity to +infinity. Okay. All right. So y equals -x cosine x. Okay. So let's say we have that. This is a particular solution to c equals 0. So if we know that c is equal to 0, we figure out c is equal to 0, we plug 0 in here for c, and of course that goes away, and this would be a particular solution. Okay, so you're going to work some differential equations, not in this section, but you're going to work some differential equations where you'll be able to figure out what c is. Okay. All right. So that's for all real values of c, the one parameter family. Notice we have our constant c there. And then if we look at this one, the two parameter family, y equals c1 e to the x plus c2 x e to the x is an explicit solution of the linear second order equation y double prime minus 2y prime plus y equals 0. Okay, that's a two parameter family solution. All right, and don't worry, you're seeing these differential equations like this and the one before. You're saying, where are they coming up with these solutions? How do they know that's the solution? How do they know that? Well, don't worry, you're going to be finding those as you go through the course. Okay, and so you can see here, this is your solution here. Well, y equals 5x e to the x. That would be a particular solution for when c1 equals 0 and c2 equals 5. If you plug those values in for c1 and c2. Another particular solution is 3e to the x. That's when c1 equals 3 and c2 equals 0. Or you could have particular solution 5e to the x minus 2x e to the x. That's when c1 would be 5 and c2 would equal 2. Okay, so that's a particular solution. You're gonna solve for c. You'll figure out what c is. All right, let's go down here. Oh, what happened? All right, I don't know what's going on, but I wrote this down. It wasn't there. It's like I guess I might have written too much on this in this area, and it's deleting it or something. I don't know, but well, anyway, we got it. All right, so let's look at using different symbols. So the functions x equals c1 cosine 4t and x equals c2 sine 4t, where c1 and c2 are arbitrary constants or parameters. Are both solutions of the linear differential equation x double prime plus 16x equals 0. All right. So if we look at this for x equal c1 cosine 4t, so what we're going to do, we're going to look at this one. Well, we've got x prime is equal to negative 4 c1 sine 4t, right? If we take the derivative, x double prime is negative 16 c1 cosine 4t. Okay, and then if we plug these into the differential equation, plug this in for the second derivative, negative 16 c1 cosine 4t plus 16 times x. So we're going to plug this in for x, c1 cosine 4t. Well, that does equal 0. Okay, we would get 0 equals 0. that would check. And then if we look at this one for x equal, let's see, what is C2 sine of 4t. So what we're going to do here is look at this solution. And then we'll have x prime is equal to 4c2 cosine 4t. And x double prime would be negative 16c2 sine 4t. And if we plug this in for the second derivative, we get negative 16c2 sine 4t plus 16. And then for x, we're going to plug this one in, c2 sine 4t. Well, you can see this side over here, whoops, equals 0. Well, this side on the left, that's 0 equals 0. That checks. And then we can also look the linear combination. And for this one, we won't go through and verify it, but the linear combination x equals c1 cosine 4t plus c2 sine 4t is also a solution. This is a 2-parameter family. Okay. All right. So this is a solution also. Okay. All right. So the next one, we're almost done. So the next example is, see, I had this written down and I don't know why it's gone. Piecewise define solution. All right. So for this one, is we say the one, we're just looking at a piecewise solution. The 1-parameter family of quartic monomial functions y equals cx to the 4th is an explicit solution of the linear first order equation x y prime minus 4y equals 0 on the interval negative infinity to positive infinity. Excuse me. So we can verify this. So we've got, here's our solution. We've got y equals cx to the 4th. So that tells us y prime is 4cx cubed. All right, so there's your first derivative, and if we take this and we plug it in, we would get x times, and then for y prime, we're going to plug this 4cx cubed minus 4 times y. Y is cx to the 4th equals 0. And you can see here, this would be 4cx to the 4th minus 4cx to the 4th equals 0. That does give us 0 equals 0. And so there you have it. All right, and we can look at the solutions. So of course, we got y equals cx to the 4th. I'm just going to write this over here, y equals cx to the 4th, just so we can see it. And we can look at, if we look at this right here, You see this? This right here is y equals x to the fourth, and this is y equals negative x to the fourth. And this correspond to the choices c equals -1 and c equals 1. So this would correspond to c equal 1, and this would correspond to c equals -1. If we can, if we figure out what c is. But here's a solution that when c equals 1, and this would be the solution when c equals -1. And from that we can, the piecewise defined differentiable function y equals -x to the fourth if x is less than 0, and x to the fourth if x is greater than 0, is also a solution to the differential equation, but cannot be obtained from the family y equals c x to the fourth by a single choice. Of c. So we can't define this by it can't be obtained from just a single choice of c. As you can see, when x is less than 0, it's -x to the fourth. When x is positive, it's just x to the fourth. Okay. The solution is constructed from the family by choosing c1 is equal to -1 for x less than 0, and c equals 1 for x greater than or equal to 0. Okay, that's where the negative and the positive come here. That's how we constructed that solution. And if you look at this graph, you can see it's just going to look like this. This is when c equals 1 and x is greater than or equal to 0, and c equals -1 when x is less than 0. See, what this would look like when c is less than 0. We're on this graph, so it's just for values of x that are negative. And then when x is positive, we're positive x to the fourth. So you can see you see we're not putting the left hand side there. It's just this for x positive. See, the dotted lines, those are hidden. Those aren't there. Okay. All right, so now the last thing, we're not going to get into this real deep, but we've got systems of differential equations, believe it or not. So it says a system of ordinary differential equations is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. For example, if x and y denote dependent variables and t denotes the independent variable, then a system of two first-order differential equations is given by this. So you've got dx dt is f of txy, dy dt equals g of txy. And a solution of a system is a pair of differential equations, x equals phi 1 of t and y, not differential equations, is a pair of differentiable functions, x equals phi of 1t and y equals phi of 2t, defined on a common interval I that satisfy each equation of the system on this interval. And I'm sure you're going to solve these systems in your class towards the end. Okay. All right. So that's the terminology and stuff. It's good to know the terminology and just kind of look at these things and see how they go. And, good luck in your class. It's really not that difficult of a class. You should be fine. You do your homework and study. But yeah, I hope you enjoyed this video. I hope it helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.